So, good evening, everyone. Welcome to the fifth live session for the course Advanced Reinforced Concrete Design offered by NPTEL. I am Harshit Agrawal, a PMRF scholar from the Department of Civil Engineering, IIT Bombay, and I will be taking weekly live session for the entire course duration. So these are like weekly sessions that we take every Tuesday from 6 p.m. to 8 p.m. We interact by answering to the questions that I will ask in the chat box, and attending these sessions regularly will help you to answer the graded assignments easily and will help you to further understand complex topics holistically. So in today's session, we will first have a recap for week 4 session that we concluded last week, and then we will review the week 5 learnings. So week 5 recordings were oriented towards understanding the flexural behavior of reinforced concrete. In this, we first had a basic overview of how a reinforced concrete system responds to a flexural force, which imparts bending in a concrete system that creates a separate zone of compression and tension. And we will understand this by looking into the stress strain relationships. Then we had a basic overview of moment curvature analysis and how moment and curvature are derived based on the strain value and the neutral axis depth. And finally, we saw the application of the theory by solving numericals to understand the moment curvature behavior and their variation with increasing reinforcement area and with changing compressive strength of concrete. Okay, so today, along with the quick theory recap for different segments, I will introduce you with several questions to challenge your understanding of the subject. So in total, we will have around 8 to 9 questions that we will discuss. Some will be theoretical, some will be numerical. And for the same moment curvature analysis, I will show you two approaches to solve the problem. One using manual calculation, and one using a simple Excel sheet calculator that I have created. Okay, at the end, I will make myself available to solve any queries related to the session or the assignments, and then we'll conclude the week. Okay, so let's start. So last week we discussed about flexural behavior of axial behavior of reinforced concrete. We idealized a reinforced concrete system with a spring-loaded mass where both concrete and steel are under an axial force, and they will elongate the same, but they will offer different stiffnesses. And what this means in RC, this means total strain in a reinforced concrete is equal to strain in concrete is equal to strain in steel, and this is known as strain compatibility. And second, the total force taken by reinforced concrete is the sum of force taken by steel and concrete. Okay, and this is known as equilibrium of internal forces. So for this, with basic equations, we derived the relationship between the axial load versus the strain. Now, for concrete and compression, we know there's a linear increase in stress with strain, then there is a plateau, and then there is a drop in stress with increasing strain. So, to represent this mathematically, for concrete having strength lower than M40 MPa, we used Hognestad relation, and for concrete having strength more than 40 MPa and less than 100 MPa, we use the Thorenfeld's relation. However, for concrete in tension, there is only a small strength gain and then a sudden rupture. So for that, we saw how we do the calculation. So we take 10% of the concrete strength as tensile strength, and we calculate the strain for that strength. And then after that strength value, we assume that concrete will no more take any load. So, since concrete is weak in tension, we use steel reinforcement in concrete. For steel reinforcement, we assume a elastic plastic profile for both compression and tension, as you can see in these figures, where the stress increases linearly with strain until there is yielding, and post yielding it becomes a constant value. So, this is the profile that we used for solving numerical. We saw step by step how to analyze a reinforced concrete or a plain concrete member when it is subjected to axial compression and tension. So first we choose a strain value for concrete. We find the corresponding strain through compatibility in steel. We so strain in concrete will be equal to strain in steel. We find the stress in concrete and steel to through the models, like respective models. We calculate the load through equilibrium condition, and we calculate the axial deformation, which is calculated as strain times the length of the member. So for this, we saw several numericals, how to use different concrete model and how to incorporate reinforcement with that also. We saw, so with increasing concrete strength from 25 MPa to 60 MPa, we saw there is a substantial increase in the compressive strength, while there is a very minimal change in the tensile capacity. However, when we add reinforcement in concrete, we saw that there is a significant increase in the tensile capacity with some increase in the compressive strength. Okay, so these were the two numericals that we saw in the last session. Okay, so now we will discuss flexural design of a reinforced concrete member. So when we talk about flexure, it means resistance to bending moment. Okay, so if you see a reinforced concrete beam placed on two supports having a p kilonewton load in the middle of the span, it will undergo deflection. Okay, now for from basic force equilibrium and moment equilibrium, we can plot the shear force diagram and bending moment diagram easily. Okay, so shear force diagram will be something like this. Okay, and bending moment diagram will be a triangular shape kind of thing. Okay, so this we know from basics that we can plot. So in this second figure, it shows the deformed profile. So this was the undeformed profile initially, how the beam will look, and this is the deformed profile after this p load has been subjected for some time, how the beam may look. Okay, so if you compare the deformed and the undeformed profile, we have two sections. There are horizontal section and there are vertical section, which are divided into grids. Okay, so you can see these vertical lines and horizontal lines, they are dividing this complete beam into grids. Okay, so in deformed profile, we can see that this horizontal line, they are becoming curved. Okay, so you can see here also, these horizontal line, they are becoming curved. Okay, as we apply load. However, vertical lines, they remain the same. So what this tells us, that there are different stress zones that are created in a reinforced concrete beam at different depth. Okay, so you can see this here. Okay, so these zones are basically compression zone and tension zone, and they are separated by a line which is known as neutral axis. Okay, so what is this neutral axis? So this is the line where the deformed and the undeformed profile will be the same in both direction. Okay, so in vertical direction, we saw there is no change. However, in horizontal direction, these profiles are becoming curved. So this, at this neutral axis, there is no elongation in the, or elongation or contraction in the length of this member. Okay, that is known as neutral axis. Okay, so above neutral axis, the zone which is present, it is known as compression zone, and below neutral axis, the zone which is present, it is known as tension zone. Okay, now what these zone means? So it means that above neutral axis, concrete is experiencing compression force. Okay, due to the loading action which is here. Okay, due to this p loading action, the concrete will be experiencing a compression force at above the neutral axis, and below neutral axis, the concrete is experiencing tensile forces. Okay, and that's why when we talk about reinforcement placement, we provide reinforcement near the bottom of a reinforced concrete system, that is in tension zone. Okay, so that's the importance about the flexural behavior of concrete. Okay, how it is dividing the reinforced concrete system into a different zone, into different zones. Now, this entire theory of zone division, stresses, neutral axis concept, it is based on elastic beam theory, which has its own sets of assumptions that needs to be taken into account during analysis of a reinforced concrete section. Okay, what are these assumptions? So first is plain concrete, plain section normal to the axis will remain plain after bending. Okay, so what this means, that strain at any point of the cross section is directly proportional to the distance from the neutral axis. Okay, so you saw here in this figure. Okay, so this is my vertical line. Okay, so as I will go away from the neutral axis, the strain will also increase proportionally. That this is what this point says. Okay, strain at any point of a cross section is directly proportional to the distance from the neutral axis. So as we go farther away from the neutral axis, the more the strain will that element in the reinforced concrete will experience. Okay, second, the maximum strain in concrete at the outermost compression fiber is taken as 0.0035. So at this topmost fiber, the strain in concrete for design, it is taken as 0.0035, the ultimate strain in concrete. Okay, tensile strength of concrete is ignored. So when we talk about this zone below neutral axis, we consider the tensile strength is just provided by the reinforcement. The contribution of concrete we take as zero, because we have seen in the axial design part also the concrete contribution is very small, so we neglect in design. The stress can be assumed as rectangular, parabolic, or any which results in accurate estimation of strength. Okay, so this concrete stress, concrete compression stress. Okay, so we saw there are different models which define how the stress of a concrete varies with strain. So it we can assume it to be rectangular, parabolic, or any of any shape, but it is required that it should give us a accurate estimation of the concrete strength in compression. Stresses in the reinforcement are divided from respective stress strain curve behavior depending upon the grade of steel. Okay, so this point we'll see when we'll talk about IS 456. So this is that stress strain profile that we get from IS 456. Okay, and the partial factor of safety that we use there. So this is regarding that the stress in the reinforcement we derive from this representative stress strain curve. Okay, and the maximum allowable strain in reinforcement at any section at failure should not be less than this value 0.002 plus Fy upon 1.15 ES. So these 2 points we will see when we will do design using IS code, not for today. Okay, so for today, the main assumptions that we need to take care of are these 4 points. Okay, and we'll understand how these 4 points contribute in the design. Okay. Now, for a particular strain in reinforced concrete, how I will find the curvature and the moment that is there in the RC section. Okay, so suppose this is my reinforced concrete beam. Okay, simply supported reinforced concrete beam, and I'm considering a very small segment dx of this beam. Okay, so if I take if I zoom this segment dx, okay, so and I assume a distance y from the neutral axis. So I've assumed this distance y from the neutral axis, okay, from the mid part, okay, from the neutral axis. It may not be in the middle, okay, it is just like from a distance y from the neutral axis. I have taken a segment. Okay, so this segment I have assumed. Okay, so what will be the strain in this segment? The strain is the change in length, okay, upon original length. Okay, so original length of this segment right now it is ds, and the change in length will be some ds dash minus ds. Okay, so this is the final length, this is the initial length of that segment. Now this initial length ds will be equal to the dx, okay, because there is no load acting initially. Okay, so neutral axis width will be equal to all the widths that are there below and above the neutral axis. Okay, so ds I can write as dx. Oh, and this will be equal to r d theta. So r is this radius, this distance of neutral axis from the top. Okay, so and d theta is the curvature that is there in the beam. Okay, so we can write ds as r d theta. However, ds dash will be something like this is the distance y, so it will be r minus y d theta. Okay, okay, so this is r minus y d theta, and d theta is our the angle that has been made. So you saw here, upon bending, there will be a curvature that will come in this beam. So about this axis, central axis, this angle which is forming, it is known as theta, that we have taken here as theta. Okay, so if we substitute these two relationship in this strain equation, we'll get this equation, and upon solving this equation we'll get that strain at this element at a distance y from the neutral axis, it will be equal to y upon r. So y is the distance of the element from the neutral axis and r is the radius, okay, of that of the that uh, curvature. Okay, so we can write curvature as phi is equal to 1 by r. This is the representation of curvature, which is nothing but strain upon the distance from the neutral axis. So this is how curvature is related to the strain and the neutral axis depth. Okay, so when we'll solve the numerical, we'll have a much better understanding how this curvature is changing with increasing strain in concrete, how the neutral axis depth is contributing to the curvature, how grade of concrete or grade of or the amount of reinforcement that we are providing is affecting the curvature. But for now, we need to remember curvature is represented by strain upon the distance from the neutral axis. Okay. Now, for the same element dx, if we know the width b and the depth h of the beam, okay, so suppose this beam that I have taken here, its width is b and its total depth is h. Okay, so at any small cross section dy of this beam, I can write the forces in the x direction, in the y direction, and the moment. Okay, so what will be the force that will act in the x direction? It will be nothing but the stress that is acting on this segment in the x direction times the area. So area is nothing but b times dy. Okay, so total force in this segment will be nothing but the integration along this vertical direction. So that's why we have went from minus h by 2 to h by 2. If I take from the middle, okay, if I assume this as origins, it will be minus h by 2 here and plus h by 2 here. Okay, so that will give me the force in the horizontal direction. Similarly, force in the vertical direction we have represented by v, which is nothing but stress acting in the vertical direction times the area. Okay, that is again b dy. So again, this is integral of minus h by 2 to h by 2 strain in y direction times the area, which is b dy. And moment is nothing but the force and the distance of that element from the this origin. Okay, so if I take an element at a distance y from this point, so the stress acting will in the x direction will be sigma xx, and the distance is y, so it is sigma xx into y into dA. Okay, so this is how we write the moment. Okay, at about a particular axis, moment will be force times the distance. Okay, so this is the same thing that we have written here. This was the force, and in this force we have multiplied the distance of that element. Okay, so at the midpoint the moment is 0. As we will go further away from the midpoint, we'll see that the y value will reach to h by 2 and the moment will also increase. Okay, so this is how we write the moment. Okay, now this stress we can write as so we know modulus of elasticity of a material is equal to stress upon strain. Okay, so we can write stress at as modulus of elasticity times strain. So this is what we have written here. Sigma xx is equal to modulus of elasticity of the material times the strain in that direction. And strain we have calculated derived from this earlier equation. It is nothing but the distance from the neutral axis upon r. Okay, so if we substitute this relationship of stress in this above equation, we'll get this relationship. Okay, and upon simplifying this relationship, so this e is not changing, r is not changing, b is not changing. Okay, so if we take e and r out and we keep this equation inside, this is nothing but it is known as the moment of inertia. So this by square dy, integral of this over the entire cross section, this is what is known as the inertia of the element. So we get e times I upon r. So that's how we get this relationship. M by m upon ei is equal to 1 by r is equal to phi. So this is how moment and curvature are related. As the moment will increase, we'll see that the curvature is also increasing. Okay, so these are the two basic fundamental equations that we saw in the live session, how they are derived and how they are related to each other. Okay, and this is the basis of elastic beam theory. Okay, that we have seen here. Okay. Now, based on the strain compatibility and the assumptions that we make in the elastic theory, try to answer these two questions. And in the meantime, if you have any doubt regarding that discussion part, you can ask. Any doubts? If not, just try to answer these two questions. So, what will be the answer for the first question? Can anyone tell me? The strain compatibility condition in flexural design implies that. Okay, so the correct answer for this will be B. Okay, so we saw when we talked about the elastic beam theory and its assumption that the strain distribution is linear across the depth. Okay, so if we take a section. Okay, if we assume this is the neutral axis depth, then across this neutral axis, the strain in the member will vary linearly, irrespective of the material. Okay, irrespective of whether they steel here or concrete here, the strain will distribution is linear across the depth. Okay, regardless of the material and non-linear linearity. Okay, so this is the first assumption that we talked when we talked about elastic beam theory. Now try to answer the second question. In elastic beam theory for a simply supported beam under pure bending, which of the following must remain valid for both under reinforced and over reinforced section? So this answer should be simple. No, for the first question, D won't be the correct answer. Steel and concrete have equal modulus. That is not true. Both are different material. Okay, there's a lot of variation in the. There's a big difference in the modulus of elasticity of steel and concrete. They are not the same. The stresses that are resisted by steel and concrete are different, like we saw in the axial behavior. The strain in steel and concrete are same at a section. So suppose my reinforcement is present at this section. Okay, so the strain acting on concrete here and reinforcement here are the same, but how much they are resisting to that strain, it is different. So we assume that the concrete contribution is zero here. It is just the contribution of steel that is coming from below the neutral axis. Okay, if we talk about this section here, we'll have the strain value, and then correspondingly we can find how much stress or how much resistance concrete is offering to that strain. Okay. Okay, so for second question, the correct answer is A. Okay, so this just the same question as the first one, just the language is changing. So irrespective of the design of the section, where is under reinforced, over reinforced, or a barren section, this condition will always remain true. Okay, it won't change. This is the basis of design. This is the basis of the design that we are discussing today, and this is the basis of the design that that you will see in IS 456 also. Okay, the strain varies linearly across the entire section. Okay. So when we talk about analysis of a reinforced concrete in flexure, so for a reinforced concrete, a strain diagrams generally looks like this. Okay, this is the strain diagram. Okay, so strain is zero at the neutral axis, and it is 0.0035 at the topmost compression fiber, and as per IS code, it is 0.002 plus 0.87 Fi upon ES at the steel reinforcement level. Okay, now here one thing to notice, this D, it is the total depth of the section, and this small d is the effective depth. So effective depth is nothing but the total depth minus the effective cover. Okay, so what cover we are providing to the reinforcement. Okay, so so you can see this strain diagram I have plotted till the reinforcement. Okay, now, in stress diagram, we have the compression zone, compression block, stress block above neutral axis, and we have the tensile strength element by the reinforcement below the neutral axis, assuming that there is zero contribution from concrete in the tension zone. So that's why below neutral axis you don't see any stress block for concrete. It is just the force that is resisted by the steel reinforcement. However, above we have a stress block for concrete, because as the strain varies, the stress offered by the concrete also varies. So that's why we saw two profiles in our previous class, the Hognestad profile and the Thorenfeld's profile. So strain, as strain is increasing from here to here, the stress in the that the concrete is offering will also change. So that's why there is a stress block profile above neutral axis offered by the concrete. Okay. So for cylindrical sample, experimentally, we know that in compression, the stress versus strain profile will look something like this. Okay. And for this, we saw Hognestad and Thorenfeld's relationship to express this profile mathematically. Okay. So if we go with this experimentally derived stress curve, then the stress block in the compression zone will vary based on the strain in concrete. Okay, so if we so it can be a linearly it can be linear. So the stress block that we saw here, okay, the shape of the stress block will depend upon the strain limit. What is the strain, up till what strain we are coming here. Okay, so it will be linear if the concrete throughout the this above neutral axis zone is experiencing a strain value of below 0.002. So suppose at the topmost fiber the strain in concrete is lower than 0.002. Okay, so what will be the strain stress profile? It will be linear like this. Okay, now it can be parabolic. Okay, if the strain at the topmost fiber reaches the value of 0.002, 0.02. Okay, so if it reaches this value point of 0.002, then my strain profile stress block will appear to be parabolic. Okay, and it can be a linear, parabolic, and decreasing if the strain at the topmost fiber exceeds 0.002 and goes up till 0.0035. Okay, so then this profile will become like this. Okay, so depending upon the strain that is acting in the concrete in the topmost fiber, my profile can change. It can be linear if my strain is going up till here, it can be parabolic if it is going up till here, and it can be a parabolic then decreasing profile if it is going up till here. Okay, so according to the strain range, my compression stress block will vary. And what will be my governing equation for all these cases to derive the relationship? There is one force equilibrium. Okay, compression force is net compression force is equal to net tension force, and there is strain compatibility. So we know this will always hold true. So at any point we can find the strain by assuming these two are similar triangles. Okay. Now when we want to calculate at which point this net compression force is acting, or what is the amount of this force, Okay, we need to have a simpler stress block. Okay, so for this stress block, calculating the net force and at which point this force is acting, it is difficult, it is complex. So instead of using this parabolic profile or this parabolic after and decreasing profile, we convert this stress block into a equivalent rectangular stress block having dimension beta 1 and alpha 1. Okay, so you can see here this stress block is something that we obtain from experimental testing, okay, for concrete. Above and for below we have just steel. Now, to simplify this concrete portion, we assume a equivalent rectangular stress block, okay, which has the dimension alpha times fc dash, this top dimension, and beta 1 times x is this dimension, okay, and x is the depth of the neutral axis from the topmost fiber. Okay, so how to find this equivalent parameters now, this alpha 1 and beta 1? Okay, so to find this equivalent parameters, we have two conditions. First criteria is the resultant force should be the same. So whatever force this stress block was offering, it should be offered by this stress block also. Okay, then only we can say we have made a equivalent stress block. Okay, so what is the force offered by this stress block? It is nothing but the entire area. What is the area of this block? So that is 0 to x, integral 0 to x fc dash into b into dy. So b dy is the area, okay, and fc dash is the force at different portions. Okay, so in integral of this is equal to the area of the stress block, which is nothing but length times the breadth. So alpha fc dash times beta 1 x into b. Okay, so this is the equation. Okay, if we equate the stress offered by this block with the stress offered by this block. Okay, now we know from experimental relationship, Hognestad relationship, fc upon fc dash is equal to this equation. So if we substitute this relationship here and we simplify the integral, we'll get alpha 1 and beta 1 will have this relationship. Okay, so this is the first relationship which we can derive. Okay, now second thing is, second criteria is at what point this force is acting. That should also be the same. It should not be like force is acting at some other point in this parabolic stress block, and in equivalent it has changed its height from distance from the neutral axis. Both the distance, the net force should be acting at the same distance from the neutral axis in both the cases. Okay, so the location of the resultant force should be the same. How we can find the location? We can find the location by multiplying, dividing the moment offered by the force times the force, entire force. Summation of moment offered by different parts of the forces times the summation of force. Okay, so for this, again with integral, we can find the moment. It is nothing but 0 to x integral force times the distance. So this is the force into b into y dy. So this will give me the moment, and summation of fc dash into b into dy will give me the force. And this is nothing but, what is the distance of this arrow from the neutral axis? It is nothing but, it is acting at the middle of this block. Okay, so since this is a rectangular stress block, then net force will act at the middle. So this is alpha by 2, and if I assume alpha is equal to beta 1 x, so x minus alpha by 2 is my distance. Okay, again in this, if I substitute this relationship, Hognestad relationship, and I simplify, I will get beta 1 as this equation. Okay, so in this way we have two equations that we can derive from just using two simple criterias, and these two equations will help us to convert this parabolic stress block into an equivalent stress block. I guess someone's mic is on. Okay, so these are like two conditions that we need to satisfy to convert a complex stress block into a simplified stress block. Okay, now So with this condition, once we get the simplified stress block element, so if we see this linear strain profile again for a reinforced concrete, so as the strain in concrete increases, the strain in steel reinforcement will also change, and accordingly the depth of neutral axis will also change. Okay, but here, it depends, like when the failure will occur. Okay, so you can see in this final diagram, as the concrete reaches the ultimate strain of 0.0035, now based on the strain in the steel reinforcement that is there at that time, there can be different types of section which are named as under reinforced section, over reinforced section, and balance section. Okay, what do you mean by these section and why they are categorized like this? So we know that the ultimate strain that is taken by concrete, okay, it is 0.0035. Now at this ultimate strain value, assuming that the strain linearity is there present, the ultimate strain that is there in the steel reinforcement, it can be lower than 0.0025, it can be equal to 0.0025, and it can be more than 0.0025. And this value, what is this value, will dictate which type of section it is. Okay, if the strain in concrete is lower than 0.0025, it means that there is no yielding that has happened in the reinforcement, there is the concrete failure that is happening before steel yielding. So that comes in the category of over reinforced section. Okay, if the strain in concrete reaches 0.0025, when the strain in if the strain in steel reaches the value of 0.0025, when the strain in concrete is 0.0035, it means it is a balanced reinforced section. The concrete is reaching its ultimate strain and the steel is reaching its yielding point at the same time. However, if steel reaches the yielding point before concrete reaches the ultimate strain value, it means that steel yielding is happening before concrete reaching the ultimate stress, and that comes in the category of under reinforced section. Okay, so here I have described all these three sections. So balance section, it is the optimum section design. Steel in tension reaches the yield strain simultaneously as the concrete reaches the failure strain. So yield strain is 0.0025 and concrete's failure strain is 0.0035. So both strain are reached simultaneously, then we say it is a balanced section. Both concrete and steel are failing together. Okay, and it is an ideal system. However, we can't obtain this section every time. Why? Because my depth of section may be irregular. When I talk about a real reinforced concrete structure, dimension may not be a whole number, it may be a like, it is difficult to like always get this value. And for getting this value, the dimension of the section that we will have to cast, they may not be a very simple dimension. Like generally we see the sections are like 200 cross 200 mm, 250 cross 250 mm, 200 cross 300 mm. But for reaching ensuring that both are failing together, the dimension can come like 215.5 mm or 218.25 mm. So those dimension we generally don't provide, we provide a whole number, we provide dimensions of a reinforced concrete in whole number. Okay, so that's why we say dimension may not be a whole number if we want to satisfy this condition. And formwork and shuttering will become complex if the dimensions are not in whole number. Okay, they are like very complex geometry or very unique to from member to member, so it will increase the cost and the repeatability problem also. Okay, so that's why to keep a simple design, generally obtaining a balance section is difficult. Now, under reinforced section, it means that steel is reaching a steel strain of 0.0025 at a load lower than the load at which concrete reaches the failure strain. Okay, so when concrete reaches this failure strain of 0.0035, steel is already crossed its yield strain value. This means that when the concrete had a strain lower than its failure strain, then only steel reached its yield strain value. And this means that steel is dictating the design or the failure. Okay, so every section should be designed under reinforced. Okay, this is what we want in our design, because as steel will yield, since it's a ductile material, it will undergo excessive cracking and deflection before ultimate failure, and that will give us a sign that the concrete has become weak, the building has become weak, and it should be evacuated or it needs to be repaired. Okay, so it gives enough time for the occupants to escape the building, because there's yielding, there's deflection is happening, there's cracking that we can see. Okay, when there's an under reinforced design, because steel is governing the failure now. Okay, so mild steel is generally more ductile than HYSD steel. So that's why, depending upon the steel grade, also the amount of deflection and the cracking, it will change. Okay. Now, the third case, that is the over reinforced section. In this, what happens? Concrete is reaching its ultimate strain value of 0.0035 before steel reaches the steel strain of 0.0025. So, what this means, that concrete crushing will start to happen even before steel at starting yielding. Okay, so this is not recommended in practice, because it will cause sudden failure of the section, because concrete is failing now before steel. Okay, since concrete fails before steel, steel won't yield much. Okay, so we won't see much deflection, much cracking in the system. There will be no warning signs that a reinforced concrete will offer, and it will undergo a sudden failure. So that's why this over reinforced section design is not recommended. So we won't get enough time for the occupants to escape the building if there's signs of uh, uh, collapse. Okay, so this is how these three design vary. Okay, balanced design is the best case, but it is difficult to obtain. Under reinforced design is what we want to make, and over reinforced design is what we want to avoid. Okay, now try to answer these three simple questions before we move into the numerical part. So, like, very simple question based on the uh, type of section that we just saw right now. In the meantime, if you have any doubt, you can ask. So, what will be the answer for question number three? A singly reinforced rectangular beam is designed for balanced failure under the limit state method. Which of the following changes will most likely convert it into a over reinforced section without altering the beam?
C, I think C.
Okay, there can be multiple answers for this. Try to think. C is a very obvious choice. Okay, we are increasing the reinforcement area, so it is becoming over reinforced. Okay, apart from this, there are two more options that can be true.
B and D also, I think.
Okay, so if you know one equation, I will just write one equation here. So this equation, it's from IS code. Okay, so I will just write, later on we'll see it again. So AST limiting, when we calculate based on I from IS code design. So it is nothing but 0.36 FCK B into depth of neutral axis divided by 0.87 times Fy. Now, so knowing this equation, just try to think. B is an obvious choice. However, This is my limiting area. Limiting area means the area which is required of the reinforcement to create a balanced section. Now, anything which will increase my area will make my design as over reinforced. Okay. So, what can be the changes that can be done? Okay. So, this is my balanced area. Okay. Suppose this value is coming out to be, okay, suppose this value is 750 mm square. This much area I require for a balanced reinforced concrete design. Okay, and I have provided 750 mm square only. Okay, that much area I have provided. Okay, now if I reduce the width of the beam, B, what will happen? This AST limiting value, it will decrease. It may become 700 or 600 or 650, but my area that I provided was 700 only. So that means that reducing the width also can make my section as a over reinforced section. Okay. Similarly, if I increase the yield strength of the steel, my limiting area, it will decrease. The area that I require of the reinforcement for a balanced design, it can also decrease. So that again can make my design as a over reinforced design. Okay. This explanation I gave based on IS 456 design methodology, but the same explanation you can get from the experimental design part also. Like when we'll see the questions today, I will try to clarify this options again, how we can think about them. Okay, when through the results that we are getting. Okay, so just remember, anything that is making the area of reinforcement more than the balanced area, that will make the design convert from balanced to over reinforced section. Okay. Question number 4. In a singly reinforced section, if the steel yields before concrete reaches the ultimate compression, which stress strain profile at failure is more appropriate? Okay, yes, the correct answer will be B. Why? Because first option we can eliminate, since concrete is not reaching its ultimate strain value, so this is not happening. Second option is true, linear strain distribution. This will hold every time. It doesn't depend upon whether it is an under reinforced section or a balanced section or an over reinforced section. Linear strain distribution will always be there, and the maximum strain in steel will exceed the yielding strain. So when we'll draw that profile at steel level, the strain will be more than the yield strain. Okay, so that is the strain profile that we will have at failure. And based on the strain that we have in steel, we can also calculate the strain in concrete, or we can do the vice versa, because we know it is linearly varying with the depth. Okay. Parabolic compression block extending beyond neutral axis, this is never possible. In uniform stress strain across tensile zone, it is also not possible. Okay. So in tensile zone, there is only at one depth at which the steel is provided where the stress is offered by the steel. It is not uniformly offered below the neutral axis. Okay, so there can be only one correct option. All that C and D option are never true. In no condition they are true. Now, question number 5. If a simplified rectangular stress block is used for a M20 grade concrete and the depth of the neutral axis is found to be less than the balanced depth, okay, then the design bending moment is most influenced by. So try to think of this question based on this relationship, strain compatibility relationship that we saw few slides ago. Okay, you need to do some calculation to understand. Okay, what is the depth of neutral axis at balance depth? Try to give it a try, assuming some section. Okay, so I will just tell you how you can think of this question, the final question. Okay, let me take one new slide. I'll eliminate the first two questions. Okay, so we know the strain compatibility equation. Now, what question says, what if the depth of neutral axis is changing? Okay, and then what will be the influence on the profile? Okay, so I know at balance section, the strain in concrete, it is 0.0035. I know the strain in steel, it is equal to 0.0025. Now, let's assume the effective depth of my member small d, it is suppose 500. Okay, I'm just taking one value. Okay, so if I know these three things, can I calculate the depth of neutral axis? Yes, from this equation I can calculate. Okay, how I will get 0.0035 times d minus x, 500 minus x, will be equal to 0.0025 times x. Okay, so this will give me x is equal to 291.67 mm. Okay, now what question says, if the depth of neutral axis is found to be less than the balance depth. So suppose if x is equal to 250 mm. Okay, then what will be the strain in steel? And suppose concrete is reaching the strain, concrete ultimate strain is remains the same. So what is the strain in steel? We can calculate again. Okay, from the same compatibility equation, it is nothing but 0.0035 the strain in concrete times 500 minus 250 divided by 250. So this value is coming out to be 0.0035. So you can see, if I will reduce the depth of neutral axis, what is happening? My steel yielding will happen before concrete reaching the ultimate strain. So this value of 0.0035, it is more than 0.0025, the yield strain of steel. So what will the correct option? Yield strength of steel and the lever arm will dictate the design. Okay, the bending moment. So we know bending moment, it is nothing but force times the lever arm distance. Okay, and this failure is governed by steel, so that's why the force, the bending moment will be governed by the yield strength of steel, what grade of steel we are using. And lever arm distance is the distance between the compression force and the tension force. Okay, so this is how we can guess what is happening. Okay, so if you don't know the answer, you can try to assume a section and get the answer, what is happening to, what change is happening to the system. Okay, did everyone understood how I solved this question?
Yes,
Any
sir.
doubts?
No, sir. No.
Okay, so let's move ahead. Now, to derive a moment curvature relationship, like how curvature and movement of a reinforced concrete section is changing at various strain that is present in the system, we need to follow a procedure. Okay, so what we know the reinforced concrete element, we know the width of the element, we know the effective depth, we know the area of reinforcement that we have provided, we know the strength of concrete and the strength grade of steel. Okay, so we'll choose one particular strain in concrete. Okay, we'll choose any value 0.0015, 0.0025, 0.0035, any value we'll choose. And using strain compatibility equation, I will get the depth of neutral axis. Okay, now what I want us to satisfy that this compatibility equation holds true. The force offered by concrete should be the force offered by steel. So net compression force should be the net tensile force. Now, at what neutral axis this will occur, I don't know. So initially, I need to assume, okay, because I can choose the strain value of concrete, but what is the strain in steel? That I don't know. Okay, and I have two variable. I also don't know x. What is the depth of neutral axis? So if you see this relationship, there are two variables to us right now. X is also variable and this strain in steel is also variable. I have assumed this and I know this. Okay, so what I will do, I will assume a value of X. Okay, some neutral axis that I will assume, and I will estimate the strain in steel using the compatibility relationship. And for the known dimension, for the known epsilon c value and epsilon c dash, we already have fixed it is 0.002 for concrete. Okay, ultimate strain in concrete. For knowing these two values, I can calculate the alpha 1 and beta 1 factor of that equivalent stress block. Okay, so in few slides ago we saw. Okay, so this we have assumed. Okay, this is the strain value of concrete we have taken. This is always fixed. Okay, so I can get beta 1 first, and once I know beta 1, I can get alpha 1. Okay, so alpha 1 and beta 1 we can get. Okay, if I know alpha 1 and beta 1, I can get the net compression force that is offered by the concrete, and if I know the strain in steel, I can get the net tensile force offered by the steel. Now, what equilibrium says that the net compression force should be equal to the net tensile force. Okay, so if it is true, then we can calculate the moment of resistance and curvature, because our depth of neutral axis that we has assumed it is correct. However, if it is not true, then what is the change that we need to make? We need to make in this assumption the whatever depth we assumed. Okay, so we can either increase this or decrease this based on the need. Okay, so that's how, this is how we do the analysis. This is an iterative process that we do. Okay, so now for the remaining two sessions, like remaining today's session also and the next session also, we'll just focus on this analysis, how this uh, whole process of deriving a moment curvature relationship is done, and how it is affected by different cases. Like what is the effect of reinforcement area when we go from an under reinforced section to a balanced section to an over reinforced section, how this profile changes. What is the effect of concrete grade, concrete compressive strength. Okay, so these 2 points we'll see today, and in the next session we'll see what is the effect of axial compression. If I apply some axial compression on the beam, what, how it will affect the moment curvature, and what is the effect of compression steel. So instead of just providing steel in the tension zone, if I provide some steel in the compression zone also, how it affects the moment curvature. Okay, so this is the entire thing that we'll discuss from now. Okay, so this is the first numerical. Okay, just to understand how this iterative process is done. Okay, just try to think of this, give it a start from this process that I described here, and then I will tell you how to do this, how to solve. So we have been given a rectangular beam of cross section 300 cross 500 mm, and it is heavily under reinforced. Okay, we have provided a very small reinforcement area at the bottom with the effective cover of 50 mm. Okay, and we need to estimate the moment versus moment capacity versus curvature profile of the section. We know the cylindrical concrete ultimate strength as 35 MPa, and we know the yield strength of steel is 500 MPa. Okay, so and we know these two assumptions. We have assumed a Hognestead relationship and elastic plastic strain relationship for steel, and we have noted the contribution of concrete in tension. Okay, just give it a try. And in the meantime, if you have any doubts, you can ask. Okay, so let me just start with the question so that we can see more questions and we can understand different approaches to design. Okay, so first couple of questions I will solve in the conventional manner. Okay, so this question I am completely describing how to solve. The next question I will just give you a short overview. Okay, where our calculations I've already done and attached. And then the third and the fourth question that I will discuss today, I will introduce to a new method based on Excel sheet, how you can quickly do the calculation. Okay, so we need to find moment versus curvature profile. Okay, so if we want to plot a moment versus curvature profile, we need to find moment and curvature at different strain levels. Okay, so let's take different strain value of concrete as point triple zero five, point double zero one, point double zero two, and point double zero three five. So at these four strain values, we'll find the moment capacity and the curvature. Okay. So first we have the lowest strain, which is point triple zero five. Okay, this is the concrete strain that I have fixed now. Okay, so you saw a couple of slides ago the procedure. First step is to choose the strain value in concrete, so that we have done. Okay. Now we don't know what is the strain in steel. Okay, so for that I need to assume a depth of neutral axis. Okay, now we have been given 500 is the capital D, the total depth of the section. So effective depth, small d, it is nothing but total depth minus the effective cover, which is given as 50 mm. So 500 minus 50, it is 450 mm. So small d we got. Okay, and B we already know the width of the member, it is 300 mm. Okay, so let's assume x at the middle. Okay, so let's assume neutral axis depth is the midpoint, that is 250 mm. Okay, 225 mm. Okay, between reinforcement level and the top, let's assume it is at the midpoint. Okay, so what is my strain compatibility relationship? Okay, I will just copy this here. Okay, so this is the relationship for strain compatibility. Okay, so sigma c I have fixed that point triple zero five. Upon x value I have fixed at 225. Sigma s is unknown to me, and capital D I know it is 450, small d is 450, and x is 225. Okay, so from this we can get the value of strain in steel, and it will come out to be point double zero five. Okay, so strain in steel is point triple zero five. Now this is very small than the yield strain of steel. So this means that steel has not yielded yet. So what will be the tensile strength of steel? We need to calculate from the linear profile. So we have already assumed that strain in steel is following elastic plastic behavior. So what is an elastic plastic behavior? It is linear up till yielding, and after yielding it becomes constant. Okay, so this is the profile and this is the profile, and this value it is point double zero two five. Okay, so if we are at any stay location at this area, then what we'll know, what will the tensile strength of steel? It is nothing but modulus of elasticity times the strain. And if we have strain more than point double zero two five, then the tensile strength of steel will become constant. It will be 500 MPa. Okay. So right now we are at a value of lower than point double zero two five. So we'll calculate the tensile strength of steel by this relationship. Okay. So TS, the tensile strength of steel, I will write as point triple zero five strain times the modulus of velocity, that is 2 into 10 to the power 5. Okay. So this value will come out to be 100 MPa. Now the tensile force we can calculate. So tensile force is nothing but strength times the area. So Ts times the area of steel, and we know the area of steel is 750 mm. Okay, so 100 into 750 mm, and for converting it into kilonewton, so I will divide by 1000. Okay, so I will get 75 kilonewton. So this is the tensile force that the steel is offering at the strain value. Okay, now for concrete, what we need to do, we need to get the first we need to get the equivalent stress block elements. Okay, so we have found these relationships earlier. Okay, for concrete stress block. Okay, one is this relationship. So I will copy this relationship here. So first was this relationship, and the second was this beta 1 relation. Okay, so we know the strain in concrete, okay, 0.0005, and we know the peak strain in concrete, that is 0.002. Okay, so epsilon c dash I will substitute as 0.002, and epsilon c will be 0.0005. Okay, similarly here also epsilon c dash is 0.0005, epsilon c is 0.0005, and epsilon c dash is 0.002. Okay, so this I will substitute here. Now first we will need to get the value of beta 1. If we will know the value of beta 1, we can find the value of alpha 1. So value of beta 1 we will find from the second equation, 0.0005 upon 0.002 here, and 0.0005 upon 0.002 here. Okay, so when you will solve this, you will get beta 1 is equal to 0.682, and when you will substitute beta 1 as 0.682 here and do solve this, you will get alpha 1 is equal to 0.336. Okay, once we know alpha 1 and beta 1, we can calculate the force in concrete. So concrete, how much force concrete is offering? So it is nothing but alpha 1 times fc dash. So 0.336 times fc dash, fc dash is 35, times beta 1, beta 1 is 0.682, times the depth of neutral axis 225 into width of the member 300. Okay, divided by 1000 to convert newton to kilonewton. Okay, this equation I will just tell you from where I have taken. So, so this is the net force that we calculated here. Okay. So this is the relationship that we are using here also. Okay. So I will just eliminate this part. So C is equal to alpha 1 fc dash into beta 1 into x into b. So when you will calculate this value of C, it will come out to be 41.37 kilonewton. Now, what is the problem here? You can see T is not equal to C. Okay, the total tensile force, it is very small compared to the total compression force. This means that whatever depth of neutral axis we have taken, it is not correct. Okay, so we need to again make a new guess of the neutral axis depth, and we again need to solve the TS value. We again need to calculate the tensile force, and we again need to calculate the compression force. And this process we need to iterate until we get these two value very close or almost equal. Okay, equal or almost equal. Now what value we should keep, whether we should increase or whether we should decrease, you can take a guess from this equation. So if you will increase the value of x, what will happen? Alpha 1 and beta 1 are the same, b is not changing, fc dash is not changing. So if I will increase x, what will happen? C will increase, but we don't want C to increase, we want it to decrease, and we want this tensile force to increase. Okay, so this is how we can take a guess what next value we need to assume. Okay, so if the compression force is more than the tension force, that means that we need to reduce the neutral axis depth. Okay, if the compression force is smaller than the tension force, that means that we need to increase the neutral axis depth. Okay, so right in this case we will right now decrease the neutral axis depth. Okay, so I will just remove this part. Strain compatibility equation will keep here because every time we need to use. Okay, so now let's assume neutral axis depth is 100, okay, or 105 mm. Okay, so what we'll get, okay, again here only one change we need to do. The depth of neutral axis become 105 here, and here again it will also become 105. Okay, so we can get the strain in steel. Okay, so strain in steel, it will come out to be 0.00164, which is still less than 0.0025. It means that the tensile force we need to calculate from modulus of elasticity times the strain, because we are lying in this zone. Okay, so it is 0.00164 times 2 into 10 to the power 5. So this will give me tensile strength of 328.57 MPa, and tensile force will become this tensile strength times the area of reinforcement, that is 750 mm square. So I will divide by 1000 to convert Newton into kilonewton. So I will get 256.43 kilonewton. Okay. For concrete compressive force, nothing is changing. Okay, B and D, alpha and beta will remain the same since the concrete strain is the same. So I can directly do the calculation. 0.336, sorry. So it is 0.336 times 35 times 0.682 into x is now 105 into 300, the width of the member, divided by 1000. So this value is 252.64. So you can see right now we are very close. The tensile force and the compression force, they have become very close to each other. They are approximately the same. Okay, so we can assume this depth of neutral axis is correct. Okay, and since the depth of neutral axis is correct, now we can calculate the moment. So moment is nothing but any one of the forces times the lever arm distance. So lever arm distance is nothing but the distance between the net tension force and the net compression force. Okay, so I will just show you in one rough sketch what this lever arm means. Just give me a second. Okay, so suppose this is my RC beam. Okay, and this is my neutral axis. Okay, so and we have plotted the stress block, strain block was this. Okay, and stress block was this. Okay, this is my concrete equivalent stress block, and this is the strain tensile force that is offered by the strain, and this is the compression net compression force offered by the concrete. So the distance between these two forces, it is known as the lever arm distance, which is represented by Z. Okay, and what will be this Z? So this total depth, I know this is D. Okay, and this is nothing but beta 1 times x by 2. Okay, this total is beta 1 x. Okay, so this is beta 1 x by 2. We know the value of beta 1, we know the value of x. So the moment of resistance, it is nothing but t times z. Okay, so it is nothing but t into d minus beta 1 x by 2. Okay, so this is how we calculate the moment. Okay, so that the same thing I will do here. So it is 246.43 times 450 minus 0.628 into x by 2. So this value will get as 102.07 kilonewton meter. Okay, and curvature, it is nothing but strain times the uh, strain upon the distance, okay, from neutral axis. Okay, so suppose I am taking curvature at the bottommost fiber, then my x, the distance, will become as the neutral axis depth. Okay, so it is 0.0005 upon 105. Okay, so this value will come out to be 4.76 into 10 to the power minus 6. Okay, so this is how we do the calculation. Okay, we first take an assumption of concrete strain. We take a concrete strain, we assume neutral axis depth, and we find whether the tensile force is becoming equal to compression force or not. If it is not becoming equal to compression force, then we need to do a iteration process. We need to again take a neutral axis depth and do the calculation until those two values become very close to each other, almost equal or equal. Okay, once they are equal, we will calculate the lever arm distance, we'll calculate the moment, and we'll calculate the curvature at the bottommost fiber. Okay, now the same process we can repeat for different strain values also: 0.001, 0.002, and 0.0035. Okay, so I have done that calculation. I will directly show you the results so that we can understand more of these application thing. Okay. So you can see here how this thing will change. Okay. So at strain of 0.000005, we got this moment value of 102.07. Now, if I will take strain in concrete as 0.001, my moment of curvature, it will go up till 155, 157 mm. 157 kilonewton meter, and after that there won't be one significant increase in the strain that is in the moment that is happening. Okay, so this is the moment curvature profile for this under reinforced section that will come, and this is how we do the calculation. Okay, this was done for 0.0005. Similar repetition you can do for 0.001, 0.002, and 0.0035 also. Okay, any doubt in this question, like how we approach the solution? Did everyone got the understanding how we apply the process, that iterative process? Any doubt in that? You're not audible. You can type if there's some audio issue. Okay, now this was a very heavily under reinforced section for which we saw the moment curvature profile. Now suppose we are keeping the same cross section, 300 cross 500, effective depth is 450, and we are changing the case. Now instead of under reinforced section, we have a balanced reinforced section. Okay, now for this balanced reinforced section, again we are calculating the moment curvature profile for these strain values of 0.0005, 0.001, 0.002, and 0.0035. Okay, so what will be the change? What you can tell me how this profile will change? Okay, whether it will decrease, okay, whether it will be like this, or like this, or like this, what will be the change? Okay, that we need to understand what is having, if what will happen if I will increase the reinforcement area. So basically from moving from under reinforced to balance section, we are increasing the reinforcement area. So what will be the change that we'll see in the reinforced concrete behavior? That is what we want to understand from here. So just try to calculate the balanced reinforcement area. How we will do this calculation? Okay, we don't know what is the balanced reinforcement area. We need to calculate it first. How to do? Can anyone tell me how we can get this area?
Yes, first we take a stress in concrete as 0.0035 and in steel 0.0025.
Yes.
According to that, we can take
And
the
like,
steel.
what is the next step then? Okay, concrete strain we have fixed at 0.0035, and in steel the strain is 0.0025 because it is in balance
Then we can
condition.
find x.
You can
Then
find
we can
x.
find x.
Okay, once you have find x, what you will do? We need to find the area of reinforcement.
Yes, after X, we can find CC, total compression in concrete.
Yeah, okay, so that is the
We
approach.
can,
Okay, you also need to
yes,
find the uh, equivalent stress block element. Okay, you know the strain in concrete, so you need to find alpha 1 and beta 1 also. If you know
beta,
alpha 1 and
yes,
beta 1, when you know the value of x, you will get the net compression force. And tension force, it is
yes,
nothing but the for stress times the area. Now, what is the stress in steel at yielding? It is 500 MPa. What is the yield strength of steel? That will be the stress in steel. So just one
yes.
thing is unknown, that is the AST. So that we can find easily. Okay. To answer your question, Khushbu, so in exam, the questions won't be this long, like plot the moment curvature profile and like that. Okay. In exam, they will just give you at the strain value, like suppose at a strain value of 0.001, find the neutral axis depth for equivalent condition, or what will be the moment of curvature at the strain if the strain is this, like that they can ask. Okay, just one at one strain value what is happening, that they can ask. Or they can ask how the profile will change if I will increase the reinforcement, how the profile will change if I will decrease the reinforcement. So that kind of theoretical questions can be asked, but for numerical they won't give you big questions. Okay, does this answer your question? Okay. Okay, so I will just tell you this process of how balanced reinforcement calculation is done, as we have discussed right now. So at balanced condition, we know both concrete and steel are reaching the extreme strain at the same time. So strain in concrete is 0.0035, strain in steel is 0.0025. Now from steel compatibility equation, I can write this equation: 0.0035 upon x is equal to 0.0025 upon 450 minus x. So I will get the depth of neutral axis. Okay, now we know C is equal to T. Okay, this is the force equilibrium condition we know. Okay, what is T? So at an extreme strain value, T is taken as 500. So we know this is the profile that we assume for steel. This is 0.0025. Okay, and we have reached this point only at balanced condition. So my tensile strength I can directly take as 500 MPa. Okay, so what is tensile force? Tensile force is tensile strength times the area. So this is my tensile force, and AST is not known to me. Okay, so this is one of my variable. Now I will move to the compression part. So for compression, I will first need to find the value of beta 1 and alpha 1. But I know what is the strain in my concrete, it is 0.0035. And what is the ultimate peak strain of concrete? It is 0.002. Okay, so substituting those values, I can get the value of beta 1 first, and then I can get the value of alpha 1. If I know the value of alpha 1 and beta 1, I know alpha 1, I know FC dash, I know beta 1, I know x, the depth of neutral axis, and I know the width of my member. So I can get the compressive force. That will come out to be like this. Okay, 2009.31. We know C is equal to T. Okay, so 2009.31 is equal to 500 times AST. Okay, so I can find the AST like I did here. Okay, so this was in kilonewton, so multiplied by 1000, I will convert it into Newton, and this 500 was Newton upon mm square. So Newton will cut Newton and Newton will get cut, and then we'll get area in mm square. Okay, so this is how we calculate the balanced reinforcement area, and this is also, it can be asked, just this part, determine the balanced reinforcement area. So you need to know what is the condition for balanced reinforcement. Okay, now, once we know the balanced reinforcement area, everything else is the same. So at this balanced condition, you can calculate the moment and the curvature. You know the depth of neutral axis, you know the tensile force, you know beta 1 and you know D. So that calculation can be easily done. However, this is when strain of concrete is equal to 0.0035. If we want to plot the moment curvature profile, we need to find multiple points so that we can create a profile. So we will again do that iterative process. I will take strain in concrete as 0.0005. I will assume a neutral axis depth. So for this depth, if you will do the calculation, you will get T is equal to 408.1 and C is equal to 541.37. Now T is less than C. So what we will do, we need to increase T and we need to decrease C. So I need to decrease the depth of my neutral axis. I need to assume a smaller value. So we will decrease X. Okay. So I assume 205. I did the calculation and I found it to be very close. Okay. So if it is close, this means that my assumption is right and I can calculate the moment and the curvature now. Okay. Similar process I repeated for 0.001. Okay. So initially I assumed 200. C was less than T this time. Okay. So what this means that I need to increase my compression force and I need to decrease my tension force. So if I want to increase compression force, I need to increase the value of X. Okay. So instead of 200, I took 211 mm and I did the calculation again. Okay, and this time C and T was very close to each other, so I can calculate the moment and I can calculate the curvature. So this is all iterative process that you need to repeat again and again and again. And one thing you need to take care is this epsilon. What is the strain in steel? If it is more than 0.0025, then yield strength will remain constant. If it is less than 0.0025, so right now it is less than 0.0025, so we need to take E times epsilon as the yield strength. Okay. As the tensile strength of steel. If this was more than, suppose it is 0.003, okay, then I won't use this. I will just assume my tensile strength of concrete is constant as 500 mp. Okay. Same I did for strain and concrete at 0.002. I did calculation multiple times until I got C is equal to T. And at neutral axis depth of 227.5, I got tensile force was very close to compression force. So I again calculated moment and curvature. Okay. So this is how I got the moment and curvature value for multiple points. And if you will plot this new data, so you can see this is for balanced condition and this is for under reinforced condition. Okay, there are two changes you can see here. One is the decrease in the curvature. Okay, and second is the increase in the moment capacity. So you can see there is a large increase in the moment capacity that is happening as we will increase the reinforcement area. Okay, and there is a large decrease in the curvature. So this curvature that is happening at the ultimate concrete strain value, it will reduce. Okay, as I will increase the area of the reinforcement. Okay. So this is the balanced reinforced concrete design. How we calculate the moment curvature for a balanced section. Any doubt in this question? How we did? So since it was a iterative method, I didn't describe the whole process again. That is just take one value, put it and get the result. Okay. Any doubt in this question or in this result?
No,
No,
sir.
sir.
No.
Okay, now every one of you will have one question that this iterative process is very lengthy. Like if you are doing assignments or anything at home where you have access to laptop, again and again doing this iterative process by pen, it takes a lot of time to get to the actual neutral axis depth. So for this, I have created one Excel sheet. Okay, for our calculation purpose. Okay, so this is the sheet that will help you to do this calculation very fast. So what is known to us? We know the cross section. Okay, we know the depth width of the beam, we know the total depth of the beam, and we know the cover. Okay, and we know the steel reinforcement area also. If we don't know, we can calculate anyhow. Okay, so these thing which is in yellow, this is known to us. Now, when we plot moment and curvature, what we do? We first assume the value of concrete strain. So suppose I am taking concrete strain as 0.0005 and small d I can calculate since I know the cover and the total depth. Okay. So what is the next step? We assume a neutral axis depth. So suppose I take as 225. Okay, so this equation here, I have placed the formula for strain compatibility. So what this is doing, based on the changing neutral axis depth and change in concrete strain, it will directly give me the strain in the steel. Okay, so you can see this is nothing but strain in concrete times d minus x upon x. Okay, that I have placed here. Now, the tensile strength of steel, it will depend upon the value of steel strain. So I have placed the if else loop here. So if else loop is like, if this value here in this block it is less than 0.00025, my strain will be calculated based on strain times the modulus of elasticity. If this value is more than 0.0025, then I will take a constant strain value of 500. So this is what I have written here. If E7 is less than 0.0025, then the stress and then the strength of tensile strength of steel is strain times the modulus of elasticity. If it is more than 0.0025 or equal to 0.0025, then the tensile strength is 500. Okay, so this is how we can simplify this pen paper calculation just by placing a if else loop. Okay, now I know the area of reinforcement. So if I know the tensile strength and in the area of reinforcement, I can calculate the tensile force. Okay, now for concrete, I know the ultimate concrete strain, that is 0.002. Okay, this is again we have already fixed, so I will place in yellow block. This is also known to us, the grade of concrete. So alpha 1 and beta 1 I can calculate. Okay, so for them I have also placed directly the equations here. So as I will change the strain in steel, this alpha 1 and beta 1 will automatically be updated. Okay, until I will make change here, these value won't change. Okay, it will only change when I will make the change in the concrete strain. Okay, so knowing all these four values, I can calculate the compression force. Okay. Now see, when my x was 225, my compressive force is more than the tensile force. So instead of doing the calculation use on pen and paper, I can just do iterative work here. So I will do, instead of 225, I will write as 200. Okay, since I need to decrease the compression force, then you can see the value here will automatically update because we have already placed all the formulas everywhere. Okay, so at 200, the it is not getting equal, I need to increase from 200, so I will place 202. Again it is not equal, 203, 203.5, 203.9, 204, 205. Okay, so in this way you can very quickly do the iteration work. Okay, okay, so you can see at 202.4 my tensile force and the compression force are very close to each other. Okay, so that pen paper thing that we were doing, that will take a lot of time to again do all this calculation and write. Using this excel sheet you can do very simply. Just update the value here, fix everything else, and just focus on these two blocks. Okay, once this is fixed, you can calculate the moment. So for moment again I have feeded the formula, and for curvature also I have feeded the formula. So once this is equal, you can record these two values. Okay, anyone has any doubt regarding this calculation sheet? Did everyone understand how this sheet is working?
Yes, sir. We understood.
Okay, so let's see how we can use this. So suppose I am taking now a over reinforced concrete. Okay, so instead of balanced reinforcement, I have taken a over reinforced. So I know the reinforcement area is 4%. Okay, so for different strain value, alpha 1, beta 1, we can fix. Okay, we can calculate also, or we know these value will be fixed. Okay, so what we'll do in this sheet, I will just enter the basic things. Okay, so B is already entered, D I know, cover is entered, small d is calculated here. Area of reinforcement, so what is the area of reinforcement? So it is 4% times the total area. So what will be the, how we'll do the calculation? So 4 times the total area, so B into D, so it is 300 into 450 divided by 100, so it is 5400. So this AST, it is 5400 square. Okay, so once I know AST, what I will do, I'll feed the value here. Okay, now for various concrete strain, we'll just see how this is changing. Okay, so I'll just show you this sheet, how I created. So I have assumed concrete strain as 0.0005. Okay, now initially I'll take the neutral axis depth as 225. Okay, so you can see at 225. Okay, no, area will be B times capital D. Okay, so I just need to calculate again. So I took the small d. It is the total area of concrete that I need to consider. So 4 into 0.01 into 300 into 500. So it is 6,000. Okay, this is not 5,400. This is 6,000. So I will just repeat 6,000 here. Okay, so you can see at neutral axis depth of 225, my steel strain is coming at 0.000005. Tensile force is not equal to the compression force. So what I did, instead of 225, to increase the compression force, I placed 250. At 250 also, it became too high. Compression force is increasing, it is more than the tensile force. So I need to decrease the value of X. I placed 240. So at 240 again I saw the compression force was not equal to the tensile force. Then I need choose one more value. So this iteration I will do quickly here and I can get the value. So at 232.5 I found that they both are very close to each other. So then we can fix 232.5 as our final result. So you can see multiple iterations, how quickly we can do the multiple iterations if we have a, if we can use Excel for calculation instead of pen and paper. So once C is equivalent to T, we can calculate moment of resistance and we can calculate the curvature. Okay. So this is for concrete strain equal to 0.0005. The same thing we can do with concrete strain equal to 0.001. Okay, again the iterative process. So I will just show you here what is changing. We will just change this concrete strain as 0.001. Okay, and at the strain I will initially take 225. It is not equal, I will increase to 240. At, you can see at 240 both are becoming equal. Okay, so this is how iteration was done. At 240 I got both is equal, so I can calculate moment and curvature. Same thing we'll do for 0.002. Okay, so first I will always place 225 just to check whether I need to increase or decrease. So right now I need to increase because compression force is less than tension force. So I will place 250. Again I need to increase because C is less than T. 255, 260. At 260 it is becoming more than tensile force. I will place some value in between. If you see at 257.2, I will get value very close to each other. So we will fix the moment and the curvature like this. Okay, and similar calculation we'll do for 0.0000035. So at 225, we will check, we need to increase. So we'll again increase. Okay. So I will go to 250. I need to increase 275. I need to increase 290. I need to increase 293.5. I need to decrease. So what will be the value? Okay, 293.25. It is becoming very close. Okay. So in this way, even some fractional value, you can do the calculation very quickly. Okay. Okay, and based on the strain in steel, you will always see changes that is happening. Okay, so you can see, since it is an over reinforced design, even when concrete is reaching its ultimate strain, the steel is not reaching the value of 0.0025. It is lower than 0.0025. Okay, so this is an over reinforced concrete design. uh, why we don't like over reinforced concrete, why we don't want over reinforced concrete to be designed. Okay, so once we know the value at different strain value, we can make the moment versus curvature plot. So you can see here, from balanced reinforcement to over reinforced, again the moment capacity is increasing, but the change is very minimal. Okay, so we can say, from under reinforced to balanced reinforced, we will see a drastic change in the moment and the curvature. However, if we will increase the area of steel beyond balanced reinforced area, the change won't be that significant. Okay, so this is how the moment and the curvature behavior they change with respect to the amount of steel reinforcement. Up till balanced reinforcement area, there will be a drastic change that can happen. However, beyond balanced reinforcement area, the change will be minimal. Okay, everyone understood how I used this Excel sheet for doing the calculation? Any doubt in this part? So if you want, I will share this Excel sheet also with you for solving the assignment questions. If you want, it will be very helpful. Any doubts in this question about over reinforced concrete design? You have my mail ID, na? So those who need, they can just drop me a mail. I will then share it with you. So you can drop me a mail
Okay, sir.
at this. You can just drop me a mail. Then I will share the Excel sheet with you. Okay. This will help you to just simply do this calculation. Okay. One more application we'll see. So this application here, we saw what was the effect of reinforcement area. So you understood that up till balanced reinforcement, there is drastic change. However, above that, the change is minimal. Now let's see what is the effect of concrete grade. Okay, so the same section I am keeping. Now, at a balanced reinforcement area, what will be the effect of concrete strength on the moment curvature behavior? Okay, so what will be the first step? First step will be to determine the balance section of reinforcement. Okay, so again, concrete strain and steel strain will fix. We know the depth of neutral axis. We know the tensile force. It is 500 times the AST. Now, for different concrete grade, my compressive strength will change, compression force will change. Okay, so for different concrete grade, my balanced reinforcement area will be different. Okay, so as the compressive strength of concrete will increase, the balanced reinforcement area is also increasing, as you can see, because this fc dash factor is increasing. Okay, so first I did this calculation. Okay, for all three cases I calculated the balanced reinforcement area. Now one by one I will do the moment curvature analysis calculation. So for M20 concrete, again we can use this sheet. Okay, I will fix the fc dash as M20. Okay, and I will take concrete strain as 0.0005. So I will first assume X as 225. So you can see compressive force is very less compared to the tensile force. So what I did, instead of 225, I did iteration. I did 220. I didn't found 210. Again, compressive force is less. 205. Again, it is less. So this reinforcement area also we need to change. Na? This is balanced reinforcement area. So what is the area? It is 2296. Okay, so this also we need to update, 2296. Okay, so at 225, compression force was more than the tensile force, so I need to decrease. So I choose 220. Again it is more, 210. Again it is more, so 203. It is very close to each other, so this is my depth of neutral axis, I can calculate moment and curvature. Okay, similar calculation we can repeat for strain value of 0.001. Again, I started with 225. I got C and T are not equal, so I did iteration. I went up till 210. I got C and T are both very close to each other, so I calculated moment and curvature. Same thing I will repeat for 0.002, 0.0035, and now this time I took one more point at 0.004. So what if the strain is beyond the strain, ultimate strain of concrete? What is the behavior? Okay, so just to check the post peak behavior, I took one more strain value. Okay, so for each of this strain in concrete, what change we need to do? Just we need to do the change in this block. Okay, this red block. Okay, we'll just do first the change in this. So at 0.004, again I started at 225. I found compression force is less than tension force. I took 230. It is still less. 250, 255, 260, 265, 275, 285. So you can see at 285 our compression force is becoming more than tension force. I will take a mid value 280. 280, again it is very close, 279. So it will be something at between 280 and 279. So in this way, upon iteration you can find 279.6. So you can see now we are very close. Tensile force and compression force are very close to each other. So this is my depth of neutral axis. So just within few seconds you can do iteration and you can solve the question. Okay, you can see 279.7. Okay, at this value the both the values are becoming very close. Okay, similar thing we can do for different grade also. So this was for M20. If I want to do the same calculation for M50, what I will do, I will just change FC dash here as 50, and I will change the area of reinforcement, balanced area of reinforcement, that is 5741. Okay, so for this I will do the calculation again. Okay, so this is how I again did for calculation at different strain value: 0.0005, 0.001, 0.002, 0.0035, and 0.004. We'll do the iteration calculation. Okay, and for M35 we have already done the calculation. Okay, so that I didn't repeat it. So you can see how the profile will come. Okay, based on the change in the concrete grade. Okay, so as the concrete grade is increasing, you can see the moment of resistance or the moment capacity is also increasing. Now there is a drop here in all the cases. Why is this drop? This is drop that is coming from 0.0035 to 0.004. So after concrete reaches the yield strain, what will happen? The ultimate strain, what will happen? The moment capacity of the section will decrease. Okay, so up till 0.0035 the moment capacity is increasing and then it is decreasing, and as the concrete grade is increasing the moment capacity is increasing, but there is no significant change in the curvature. Okay, so if you see at 0.004, the curvature in all is almost the same. Okay. However, for below at 0.0035, the curvature is increasing. Okay. As the concrete grade is increasing. So this point, and this point. These three are for 0.0035. So you can see the curvature is increasing. Here also you can see there is a slight increase. Here also there is a very slight increase. Here it is almost the same. Okay, here it is showing slight increase. Okay, so mainly the change happens is in the moment capacity and not in the curvature. However, when we talked about increasing reinforcement area, we saw the curvature was also decreasing drastically and the moment capacity was also increasing drastically. So this is how concrete grade and steel reinforcement area differ in their impact on the moment curvature behavior of a reinforced concrete system. Okay, everyone clear with this question? Like what final conclusion we are getting and how we did the analysis? Any doubt in this question?
No, sir.
Okay, so this was all for today. So we had a basic overview of flexural behavior of reinforced concrete. We understood the stress versus strain response. We understood elastic beam theory and its assumption. We discussed the derivation of moment and curvature, and we saw how they are related to each other. And we looked into how implementation of this theory base for different types of section based on reinforcement area and how they affect the reinforcement area and concrete strength, and how they affect the moment and curvature. And we talked about failure also. What is the failure in over reinforced section, under reinforced section, and balance section? Okay, so next week we'll just build up on this. Now we'll add compression force, we'll add compression steel, and this Excel sheet also we'll see how we can update this sheet. Okay, so when we add compression force, how to account for compression force, how to account for compression steel, how to make changes to the simple sheet so that we can simplify any type of problem. Okay, so that also we'll see in the next session. For now I will just ask you, you can take the sheet from me but try to create it on your own also, so that you understood how I so that you can understand how I placed every element in their position, and how I used all the relationships that we have derived today. Okay, just give it a try, else I will share the sheet. Okay, so this was all for today. Okay, thank you. Now, if anyone has any doubt regarding any assignment or any other question regarding the session that we had today, they can discuss.